Talking about differentiation rules. So a quicker way to differentiate things and an easier way than using first principles, which we looked at last time. So before we get started, however, there's a couple of things I need to mention. So far, the notation we've been using has been saying that f of x is some sort of function, and then our derivative, or our gradient function, is f dash of x. So that's the notation we've been using, and this notation has actually been used by a guy called Lagrange, a famous mathematician. But there's also another type of notation that gets used as well. And it's if instead of using the f of x equals a function notation, so instead of using this function notation, you can use the more sort of relation notation of y equals something or other, and then your derivative is dy dx. And this is a notation sort of favoured by a different guy called Leibniz. So there's another way you might find a derivative. And in fact, there are others as well. So if we just have a quick little look at some others. Here's a bunch of them. So here's Leibniz's one. He likes the dy dx style. And here's Lagrange. He likes the f dash of x. And you can see there's others too. So there's one that Euler likes, and there's also one that Isaac Newton liked down here as well. So you may see some of these different forms of notation coming around. So if you look at them over here on the right, we've got our f dash of x one. This one won't really get mentioned in this course. This one might, where there's the dot on the top. And there's the f of x. That one won't really get mentioned too much either. So there we go. Thought I should mention that before we begin. Since we're here as well, another thing is that there's a big debate about who invented calculus. And was it either this guy called Leibniz, who's been using this dy dx notation, or was it in fact Isaac Newton who used this x dot notation or y dot notation over here? I might talk a little bit about that in class, but as it's actually kind of an interesting tale. So if you want to check it out, check out this guy's channel, Got the Gist, and type in the calculus controversy. Pretty interesting. So throw that out there, check it out for yourself. Anyhow, the whole point of that was just to show you that we have some different notation, and I'll try and use them both interchangeably to give you a good vibe for them. There is one other that's actually going to be a little bit common soon, which is sort of combining the two. So you could have actually this derivative being df of x dx. Okay, so it's like this second one, but replacing the y with the f of x bit. So you may see that one around a little bit as well. But they're the three key ones to think about. Okay, now to get into the meat of this video, which is talking about differentiation rules. The first one is the most important one, and it's basically saying that if we have a function that looks like x to the power of something, so let's just say x to the power of n, that means its derivative, f dash of x, will be n times x to the power n minus 1. Okay, so what's happened is the n has come down out the front of x, down the front, and then whatever n was, it's going to be something one lower power. So let's do a couple of examples to get this into people's minds. So suppose our function is x to the power 3. That means f dash of x, our derivative function, will be 3, it's come down, and then x, and then 1 less than 3 is 2. There we go, so our derivative function is 3x squared. Let's do a couple more. This time I'll use the other notation. So suppose we've got a function y equals x squared. So this time dy dx, our derivative, the 2 comes out the front, and then it's x, and 2 take away 1 is 1, so it's just 2x. Alright, let's do one more example. Oh, actually we'll do 2 more. So let's this time have y equals 7. Okay, now think carefully, because this one's a little bit tricky, because what you've got to think is that 7 is actually 7 times x to the power 0. Okay, so this time dy dx is 7 what's my train of thought here? Is the 0 comes down, so we've got 7 times 0, and then we've got an x minus 1. Now you notice that 7 times 0 is 0, so overall this whole thing equals 0. So our conclusion is that if you've just got a constant term, so if we have a function that is equal to just a constant term, the derivative is actually 0. Oh, sorry, I've done the inverse. Whoops. The derivative is 0 for a constant term. Okay, let's do a couple more key examples. So this time we'll have y is equal to just x. This time dy dx. Well, it's like there's a silent 1 here. So that 1 will come down the front, and then we'll have x to the power 0. It's 1 take away 1 is 0, and x to the power 0 is just 1. So that one, this time the derivative is just 1. Okay, one last example. So if we have our function, and perhaps our function is equal to 1 divided by x squared. Okay, now this one looks a little bit different. It doesn't just look like x to the power n. But it could look like that if we cleverly changed it to x to the power minus 2. So now we're ready to use our little rule. Our derivative function. Sorry, let me fix that up. There we go. Alright, our derivative function is equal to the minus 2 comes out the front, minus 2, and then x to the power of minus 2 take away 1 gives minus 3. Which of course, if you want to, you could write that as minus 2 on x cubed. So there you go, there's a whole large selection of common examples for you. Okay, let's jump ahead now to the second differentiation rule. Alright, so rule 2. It basically says that if you have, if your function f of x is equal to some constant times x to the power n, so this is the same, just with a constant term out the front, then that means your derivative function, oh man, I keep doing that. Let me just do that again. Our derivative function, f dash of x, is actually just equal to the constant term, and then do the same thing as before. Okay, so all it really means is the constant term just sticks around. So to do an example for you, if our function is, let's say 4 times x to the power 3, that means our derivative function, f dash of x, well, the 3 comes out, so it makes that 4 times 3x, 3 take away 1, squared. Which is then 4 times 3 is 12x squared. Okay, fairly basic. Now let me do one more example just to get this fully in your minds. So let's say our function y is 2x to the power 6. That means our derivative function, dy dx, will be 6 times 2, which is 12, x to the power 5, because 5 is 1 less than 6. Okay, so that one's fairly basic, so we'll move on ahead to our third and our final differentiation rule, which basically says if our function, our original function, is actually made up of two parts, one function plus another one. In this case, our our derivative function is just equal to the two derivative parts added together. Okay, so this is pretty much what you'd expect, really. So I'll give you a couple of examples of this, just to show you what I mean. So it means if our function is, say, x to the power of 4 plus x to the power of 2, oh, let's make that 3x to the power 2 plus 1, then our derivative function is just the derivative of the first bit here, so that's 4x to the power 3, plus the derivative of this bit here, which is 2 times 3, 6, and then x and 2 take away 1, so that's just a 1 there. And the plus the derivative of a 1, which is 0, because that's just a constant term. So there we go, there's our final answer. Now, of course, we could have written this in terms of our other notation as well. So I'll just do that for you quickly so you've seen it at least once. Just using our other notation, the same rule, you could have written y equals, g plus h. That means that dy dx just equals dg dx plus dh dx, which is just the exact same thing as our rule 3 here. These are exactly the same rule, just written in the different notation. Okay, that's everything for this video. So go ahead and get lots of practice, and you'll soon find that it's super easy just using these simple rules. Alrighty, see you later.